All right, good. Well, I didn't know what Chase was going to talk about, but my mind is just buzzing with his thoughts, because what we're going to look at is a way to make a change in how we build software. I think about this as what I would call building on rock, building on strong mathematical foundations. You know, I've been in this business a long time. I actually started out on the Apollo project, believe it or not, and we programmed the Saturn V launch vehicle. We programmed the ascent to orbit and the translunar injection back in the day. And the Saturn V had 3 guidance computers that were in a triple modular redundant configuration with voting logic. They weighed about 70 pounds apiece, and they were blazingly fast at about 12,000 instructions a second. So the next time you see a clip of a Saturn V lifting off and heading downrange on a moon mission, that's our code doing its work. Before I leave that subject, fun fact about the Saturn: from the time it left the pad until the time it cleared the tower, which is a few hundred feet, it burned 140 tons of propellant. A serious machine. But I've spent almost all of my career helping to develop strong foundations for software development and verification. And what we're doing right now is we have a startup that is working on a new technology called software behavior computation. And we're going to take a look at this. This is something really new and different. You may be seeing this for the first time. I mean, I've just been seeing it recently myself. But it is a new approach. And I want to just start, let's see, let me just, I want to start thinking about things that we intuitively understand, I think, in our careers, but sometimes it's worth making them explicit and really having a conversation about them. In the past 30, 40 years, software has come to dwarf hardware for example, in cost allocation. That first bullet there, that's NASA. Hardware to software cost ratio back in the 80s was about 10 to 1. You'd build a system and then you throw some software into it. Well, now you build a system and the software is just so much more complex and costly. The ratio is now about 1 to 2. If you look at parts count, think about this. A software system is composed of instructions, obviously. Every instruction has the possibility of failure. So it's a part. A software instruction is a part in a complex cyber-physical system. Well, it's very hard to get solid data about parts counts in cyber-physical systems because they're built by contractors and they're not interested in much in publishing these things. But I have been able to dig out a little bit on the F-35. These numbers may be wrong, but in general, we're talking about a machine that's got about 300,000 hardware parts and at least 8 million software parts. I've seen numbers as high as 24 million lines of code, parts for the F-35. So it's a ratio of about 25 to 1. So this quote from, this is NASA 5 years ago, in testimony to Congress, saying that, hey, we don't build hardware and install software anymore. We build software systems and wrap some hardware around it. So what we're seeing is that the work that we do is becoming more and more important all the time because we are the driving force factor in all of these cyber-physical systems, the kinds of things that Chase was talking about. And the responsibility that we have is just absolutely enormous. Now, I want to, everybody wants code that runs right, systems that work all the time. There's no loss of effort. There's such effort and time and money put into trying to ensure correctness, trying to ensure security, and yet failures continue to occur. I was at the AIAA Ascend conference last week. I gave a paper there, and I was talking to some people from Boeing. You may remember a couple years ago, the Boeing Starliner was launched on a test mission, no astronauts on board, and it failed to achieve the proper orbit. It burned up all its maneuvering fuel in some crazy situation because of a software error. Now think about that. Boeing took a $600 million write-off because of a software error. One error. You look at the CrowdStrike disaster. That's going to be $1 trillion failure by the time it's all added up. In fact, Delta Airlines recently stated that they took a $500 million charge because of the CrowdStrike error. If you look at take a look. It's worth taking a look at the Consortium for Information and Software Quality. They do pretty good work. They're pretty thorough. Astonishing findings out of that. Poor quality software is costing a couple $1 trillion a year in the U.S. But again, it's not because we're not putting a lot of effort into it. Nobody wants to see these things. So the question is, it's like Chase said, look, you do the same thing over and over again, you get the same result. And I want to talk with you a little bit about some 800-pound gorillas. Testing is the principal means of software assurance. Since the dawn of computing, what could be more natural than you write the code and you run it, you test it. It's been around as long as software. It's been around for 75 years or more. And yet, it's well understood that testing can only show the presence of errors and not their absence. Not possible. And testing can only exercise a small fraction of possible executions, which in programs of any size are just uncountable. So we've been depending on testing, and we've built this whole very elaborate set of tools and processes, all based on testing. And it's all good stuff. There's nothing wrong with it, but it has some intrinsic limitations. And we need to think about how do we get beyond that. Static analysis has been around forever. Syntactic analysis of programs. Well, static analysis has a tough time understanding what loops do. And so if you look at the static analysis tools that are in use today, virtually all of them unroll the loops a couple of iterations to get an approximation of what they're doing, which is guaranteed to be wrong. Human reviews, you've got human fallibility, attention span, as Chase talked about. Formal methods can be made to work, but boy, they cost a lot and they take forever, and they're just not practical for large-scale industrial use. So all of these things are vital. We're not going to stop doing it. We'd be crazy to stop doing these things. But we have to ask ourselves, can we get beyond this? Now, what we're trying to do is develop a new approach that I think is going to, hopefully, will make a difference. We're developing math foundations, building on rock, to be able to compute what software does. That is, to be able to take in a piece of code and compute everything it does and tell you about it. Answers the question, what does this code do? Now, this is an emerging technology. Computing the behavior of software is not easy, or else we'd have all kinds of behavior computation systems around that we could make use of. It's not easy, but it can be done. And this technology has certain properties which are really valuable. The computations are domain to range. Everything in the domain mapped into everything in the range. So there's no behavior left out. It's all there. And one computation like this subsumes all tests you could run against the code. It shows the behavior that there's nothing left out. It also shows you how the results are computed. If you run a piece of code and you test it, you get an answer out, it says 7. Okay, 7, how was that computed? Testing doesn't much tell you that. So this process enables a new approach to verification and security analysis, and it's made possible by a breakthrough in how to compute the behavior of loops, which has been a problem that's resisted academic solution for decades. None of this is easy, none of this is simple, but we're trying to move in this direction. Now, what you get out of this process, this function extraction process, is you get the as-built specification of the code. You get a definition of how the code changes the initial state into the final state. So if you're a user, you don't have to write a spec. You certainly should, and we ought to be specifying our systems and doing much more with that. But this tells you what the code does in a specification form, non-procedural form. And it allows you to verify that without learning a whole lot about verification methods. You're able to look at the behavior and say, yeah, this is what we want, this is not what we want. So it's a whole different approach. And again, I want to emphasize, this is embryonic, it's emerging, none of this is easy. But in general, the way a function extraction system operates, it takes in source code, could be in any C-like language, and at any origin. Is it new development? Is it legacy stuff? Is it open source, vendor, whatever it is, it doesn't matter. It just processes code, whatever its provenance and history. And this is mathematically precise. And then you get the as-built spec, you get the full behavior. And another thing about this is, because it computes all the behavior, if there's malicious content in there, it's toast. You know it. You're going to find it because it's just more behavior. So this is what we're trying to do. The process itself makes use of the mathematics of invariant relations for loop computations. And there's a lot of complexity in that, but we are able to compute the behavior of loops, and then basically what we do is convert the program into a set of equations. We then go to an equation solver like Mathematica, and we get the behavior. Now, I want to show you, we tried to put together the most complex mess of code we could possibly imagine that would still fit on a chart. So here's this disaster. There are no semantic clues in it at all. There are no comments. The variable names are meaningless. What does this program do? I have no idea. I'm sure somebody here has already figured it out. So let me know if you've cracked the code here. It would take a human, take a person, a few days, I would guess, to work through this, and a good chance they'd be wrong. So I'm going to show you now what gets computed in terms of the behavior. And this was produced by a function extraction prototype. Hands off, no human intervention at all. And this is important here because it shows you the canonical form of behavior computation. The canonical form is a conditional concurrent assignment. And any program that you put through this process is going to be expressed then in terms of it's non-procedural, these are concurrent statements, and they're conditioned on whatever has been computed. So if you take a look at this, you see that in the program there are two cases of behavior. The first case, the condition is I greater than J. And then on the right there, you see a series of assignments. The P stands for prime. So that means it's the new value, the final value. So you're expressing final range values in terms of domain values. And every state variable is accounted for in that computation. Now, you take a look at this and say, holy cow, that case has got some really obscure exponentiation going on and so on. This is difficult stuff for a human to figure out. In the second case, the condition is different. And in that case, again, the behavior is different. Looking at operations with Fibonacci series and so on and so forth. So all of this was computed in a few seconds. Now, by the FX prototype. Now, I'll show you something else here. Here's a little program that, it's the mod function. It's like, gives you the remainder of long division. That's a few lines of code, and maybe this thing sits way down in the deep regions of some system, and it hasn't been looked at for 20 years. It just gives you the answer. You want a mod value, you run this thing, and there it is. We ran 10 billion tests against the program on the left, and they all passed. It all worked. The FX, this function extraction computation, showed, yeah, there it is. There's the mod. There's the mod function being correctly done. But if you look at the program on the right, there's some other kind of stuff in there. There's some a comparison to a numeric string, and if that is satisfied, if a crazy numeric string comes in, it sets the remainder to 9. Both of these programs passed the 10 billion tests. The 10 billion tests didn't find that malicious content. But the computation of behavior shows that, hey, now we've got 2 cases of behavior. There should only be 1. The first case has this extra crazy test on this numeric string. If that part of it fails, it gives you the right answer. But in case 2, it sets the remainder to 9. So you can't hide this stuff from behavior computation. Now, this is a more complex example. This example was done by the FX prototype plus some human intervention. Because this is a real world program. This is fairly difficult stuff to work through. I think everybody here knows what a controller is. I mean, you've got one on your thermostat in your house and so forth. And controllers are ubiquitous across every discipline you can imagine on a global scale. They control everything: temperature, pressure, volume, you name it. And the way a controller works, it has sensors that, for example, sense temperature. And then if the temperature is out of bounds and so on, it actuates heating or cooling, whatever it is, to keep the temperature within some range. Most of these controllers are pretty simple-minded things, like you have in your own home thermostat. But this particular flavor of controller uses 3 different computations and combines them in a way that allows the controller to have very smoothly functioning approximations to the temperature or pressure that you're after. It smooths things out. It simplifies. It's not so like step functions and so on. So the controller keeps a history of its computations and so on and so forth, and it's fairly complex stuff. Now, so here's the result. And I'm not going to go into any of the details here, but there's a proportional term, which is just a difference of current and prior responses. There's an integral term. You can see a summation sign there, which is approximating the integral. And you can see a derivative term that is looking at how fast it's changing and so on. So if you're a control engineer, I mean, you would love to see this, because this is what it really does. And if you don't want this, you now have an opportunity to change and redo it. Now, all of this scales up in a fairly systematic way. If you've got a hierarchy of programs, you compute the behavior of the leaf nodes and you propagate that up, and you keep propagating all the way until you get the behavior of the full system. Now, I also, one of the things that we're really concerned about is AI-generated code, and how that gets, or if it gets, verified. There are lots of processes being used today and experimented with in how to make this work. But in general, there's a requirement, and then there's an initial prompt to an LLM to generate code. And then once that's been generated, the user can look at it, they can test it, do whatever they want, and decide, well, this isn't quite what I want, so I'm gonna refine the prompt. And I keep moving in this empirical loop. There's just empirical stuff going on, and eventually I hopefully get to something I want. Well, that's okay, but what we would like to be able to do in the future is interrupt that cycle by computing the behavior of the generated code on each time through the loop, so that the user now has definitive knowledge of what the code is doing and is in a position to change, modify whatever is necessary. And so both of these loops, they're now definitive. So we're as I said, we're very concerned about this, and we really want to be able to help and contribute to the integration of AI into software engineering, but to do it in a way where we're able to use the mathematical foundations of software engineering to help guide that process. Now, at the bottom of this chart there, you see there are 4 function operators that are associated with behavior computation. I'm not going to go into that. That's all beyond the scope of what we want to talk about today. But those operators can be used by a programmer or software engineer, can be inserted into the code to help the user verify that the code is right. And there's all kinds of checks and so on that are being done automatically because you've got the computed behavior available to you. So in any event, we're hoping that that will be useful and important. But we'll see. Now, there's another thing we're looking at in terms of education. We all know that the educational process in programming and so on involves, at the university level or whatever, you learn how to write code, and then maybe next year, if you're lucky, you get a course on how to verify code. This is a crazy, insane thing. I mean, no other engineering discipline in the world would tolerate that. I mean, you want to fly on airplanes that have never been verified? You want to drive trucks over bridges, see if they work? It's laughable. So what we're interested in doing is bringing those two things together. Let's create the code, but let's verify it on the spot before we go on, so that people learn how to write correct code instead of just writing code and then finding out later on maybe they can do something about correctness. Now, so where are we? We have a proof of theory prototype. I showed you some examples that were produced by that. We're building up what I call a proof of implementation prototype, which takes into account all the idiosyncrasies and crazy semantics of languages like C. Once we've got that up and running, then we're in a position to build the full system. Now, all of this is not just, it's not for the sake of technology, it's for the sake of large-scale endeavors in industry and in government. It's for management, it's for strategy, it's for the larger things. If you're able to build software that works right, then you're able to do a whole lot of things as Chase pointed out. So we think there's a real advantage to be able to do this. And the educational payoff, obviously, is you get people who can write code and know that it's right. So we're happy to talk with organizations and people in terms of partnering and pilot projects and so on. So that's what we're doing. That's my story. Thank you.
I don't mean to sound confrontational, but how would you reconcile this with people who take direct output from an LLM and plug it in without even verifying it? There's also Knuth's quote of, "Beware of the above code, there may be bugs in it. I've only proven it correct, not run it." So well, I'm afraid, you're saying that this proves that the behavior will do what we expect. But, if people just accept it for what it is without verifying it, that could lead to problems.
Well, one of the things that terrifies us and is going on all the time today is people get code out of an LLM and they throw it into production. They don't even look at it. God help us. So we're trying to intervene. We're trying to do an intervention there to say, look, don't do that. Run it through a behavior computation and take a look at what you've got. Now, if you don't think the behavior computation is correct, then you can build a test oracle based on that behavior, and you can test the living daylights out of it. We've done that. We've done that, and the tests always work. So I mean, you're bringing up the key technical and societal issue in the use of AI. And as I said, it's a terrifying thing, and we need to be looking at that and how to be constructive in improving that situation. Yeah.
Hey, how's it going? I liked your presentation. A quick question regarding behavioral process. What's your opinion regarding bad source code into the AI process for behavioral computation?
I mean, that's another big issue with AI in this domain. It gets trained on good, bad, and ugly code. That's what it knows. Another related issue there is that if that's all it's got to work on, how's it ever going to do anything new? It's just looking at old stuff. So there's all kinds of issues swirling around this that we really need to come to grips with quickly.
In terms of implementation, what would this look like if somebody were to try to plug it into a pipeline, maybe for a system that they're already doing formal methods on? How would that potentially compare to formal methods and processing time? Would this speed up certification? Would it take the place of formal methods?
Yeah, I mean, I think this is I'd call this an implementation of a formal method. And I think that in terms of that kind of a pipeline, it just fits in naturally. I mean, your goal is to correct code, and here's a way to help you achieve that, and I think just natural progression.
So, I mean, I was just wondering, the outputs of this FX verification, are they something that can be consumed by a computation to make sure that it meets the expected behavior, or is it something that has to be reviewed by human?
Well, what we produce as computed behavior is the result. Now, I showed you the raw output. Mm-hmm. In a real system, this would be sugar-coated and graphical and so on and so forth, so that it would be a lot easier for uninitiated users to pick this up and use it. But yeah, that is the result.